Listen up, cadets. As your examiner, I'm going to hit you with a hard truth right out of the gate. Miscalculating stability doesn't just mean bombing your written exam. Out on the water, a simple math error can have absolutely devastating real-world consequences. Seriously, the maritime courts are literally overflowing with cases where a tiny misjudgment resulted in ships grounding, colliding, or just completely capsizing.
So, welcome to this explainer. Today, we're adopting a strict zero-tolerance policy for confusion. We are taking those dense, heavy naval architecture textbooks, the standard guides for masters and mates, and transforming them into a high-yield study guide. My ultimate goal here is to make sure you master the critical math and physics required, not just to pass my oral exams, but to keep your ship afloat and your crew safe when the weather takes a nasty turn.
Okay, here's our battle plan for the explainer. We've got 4 crucial areas to cover. First up, flotation and basic stability. Then we'll look at draft surveys and dead weight. After that, we'll tackle some specimen examination questions. And finally, we'll wrap up with the revision one-liners. Right, let's dive straight into Section 1, flotation and basic stability. Okay, so the absolute bedrock of all this is understanding the metacentric height, which we commonly call GM. This single metric is the foundation of the whole shebang. It's the ultimate deciding factor in whether your vessel stays in a stable equilibrium, safely rolling and returning upright, or if it suffers a dangerous angle of lull. An angle of lull is basically when it just flops over to one side because it lacks the internal forces to right itself. Look, if you don't know your GM, you just don't know your ship. And this image right here brilliantly illustrates the internal mechanics at play. Notice how the downward force of gravity, acting right through the center of gravity, and the upward push of buoyancy from the center of buoyancy, see how they shift as the ship heels over? These opposing parallel forces create what we call a moment, specifically the righting lever, or GZ. This lever is literally the physical force yanking your ship back to safety. Now, to understand how this actually feels out on the deck, think of a stiff ship with a really large GM. It's a lot like a sports car with a stiff suspension. It hugs the road, sure, but it has a fast, snappy, and frankly uncomfortable roll. On the flip side, we have a tender ship with a small GM. This kind of vessel rolls sluggishly and takes a sweet time returning to upright. It's exactly like a heavy, top-loaded moving van trying to take a sharp corner. You absolutely need to know which one you're commanding before you ever leave port.
Moving right along, let's hit Section 2, draft surveys and dead weight. So to perform a mathematically accurate draft survey, you definitely cannot just eyeball the waterline and call it a day. You've got to follow these precise steps. First, you correct your observed drafts to the forward and after perpendiculars. Second, you correct your midship draft for hull deflection. And only after doing all that can you calculate your true mean draft. You literally must have this true mean draft in hand before you even think about glancing at your dead weight scale. Now, visualizing this hull deflection is genuinely fascinating. A massive steel ship actually bends depending on exactly how you load it. Those dashed lines show you exactly what I'm talking about. Knowing whether your ship is sagging, meaning it's heavy in the middle, or hogging, meaning it's heavy at the ends, is absolutely vital for getting that true mean draft right. If you ignore this, well, your cargo calculations are going to be completely out the window. Okay, so once you've painstakingly calculated that true mean draft, you'll consult your hydrostatic particulars, kind of like the standard TS00272 table here. Let's look at this specific row. At a 7-meter draft, you can extract your displacement, your tons per centimeter, or TPC, and your moment to change trim, 1 centimeter, or MCTC. Honestly, you can think of this table as your ship's basic DNA. All right, on to Section 3, specimen examination questions. Let me be clear. In my exam room, you are guaranteed to face some pretty complex scenarios. You've got to be able to calculate the final vertical position of the center of gravity. That's your new kg, after loading, discharging, or shifting heavy weights around with the ship's gear. Plus, you'll be heavily tested on the free surface effect. If you've got slack tanks, that sloshing liquid creates a virtual loss of GM that can literally capsize you. You have to prove to me that you can correct for it mathematically. Oh, and here's a classic examiner favorite. I will absolutely ask you to calculate the virtual loss of metacentric height during the supercritical period of dry docking. See, the exact moment your ship takes the blocks fore and aft, but before the dock is fully pumped dry, there's this massive upward push from the blocks. It acts exactly like a weight being removed from the lowest point of the ship. This causes a terrifying virtual rise in your center of gravity. You have to calculate if your ship's going to remain stable or if it's just going to fall right off the blocks.
Let's wrap things up with Section 4, the revision one-liners. All right, let's see how sharp you are under pressure. This is a rapid-fire drill. Question 1. Answer quickly. What is another name for the kg? The answer is the vertical center of gravity, or VCG. It tells us exactly where the total weight of your ship pushes down, and honestly, it's the anchor point for all your stability math. Next question. What exactly is a hydrometer used for when you're out there on deck? It measures water density. This is absolutely essential for calculating the change in your draft when your vessel moves from, say, brackish stock water out into dense salt water, using the freshwater allowance. If you forget to use this, you're going to totally miscalculate your load lines. Okay, third flashcard, and this one is pure math. If your angle of heel is less than 10 degrees, what is the mathematical equation for the righting lever GZ? Well, the righting lever, GZ, equals the initial metacentric height, GM, multiplied by the sine of the angle of heel, theta. Sure, it's just simple trigonometry, but trust me, it saves lives. And finally, our last quickfire question for today. What are the formulae for tons per centimeter and moment to change trim 1 centimeter for a ship floating in standard saltwater?
For TPC, it's your vessel's waterplane area divided by 97.56. This brilliantly highlights exactly how your specific hull form, right at the waterline, directly dictates your loading capacity centimeter by centimeter.
I'm going to leave you with this final, absolutely critical thought. Mastering this math, it isn't just some academic exercise to pass a test or please an examiner like me. It's about asking yourself, what really happens to your ship, your cargo, and your crew if you fail to respect the laws of stability at sea? A negative initial GM leading to an angle of lull is basically a death sentence in heavy weather. So take this knowledge, apply it diligently, and keep your vessels safe out there. Thanks for joining me on this explainer.